Good morning and welcome to this course which is called Vibrations of Plates and Shells. Vibrations of plates and shells. Essentially it's a course on vibrations of continuous systems. My name is Venkata Sonti. I am a faculty in the mechanical engineering department at IISc, and I work in the area of acoustics and vibrations. I teach this course here, and hence I thought I will record it for NPTEL. Now there are other courses on NPTEL that relate to a similar topic, vibrations of structures. So there will be some overlap with that material. Okay. However, regarding this course, how it is structured is first that we will look a little bit into differential geometry. Okay, of surfaces, that is. For this part I will use the textbook by H. Krauss titled Thin Elastic Shells. Then the idea is using general shell properties. General shell descriptors, that is, descriptors, which are the Lemay parameters, and radii of curvature. We will derive a general set of equations of motion. Using the Hamilton's law. Okay. For the general shell we will figure out the potential energy, the kinetic energy, any other energies coming from boundaries or forces and external forces. Formulate the action integral, and derive a general set of equations. Okay. That means whether it be a beam, a straight beam or a curved beam, a ring or a rectangular plate or a circular plate, or a cylindrical shell or a conical shell or a toroidal shell, any other shell which is a shell of revolution, actually shell of revolution. Okay, which can be described by these parameters, Lemay parameter and radii of curvature. You will have one set of general equations. You do not have to derive again for a beam, for a curved beam ring, again and again you do not have to. That is the difference largely from other courses. Okay. So now once you have the general set of equations, you substitute these Lemay parameters A1, A2, R1, R2, and out will fall the particular equations for that particular shell. Okay. And so you can do this calculation symbolically. Okay. If you know a symbolic package, you can program these equations in there. On the top you described A1, A2, R1, R2, and then out will come out the specific equations. Okay, so that's the main angle over here. Okay. Now what is the textbook, or let me continue. So once we have the equations, okay, we will compute mode shapes and resonances or natural frequencies for a certain set of geometries in the closed form. Okay, that means analytically. That is one part of the thing. Then if one cannot come up with closed form analytical shapes, we use the method of Rayleigh-Ritz. Rayleigh and Ritz method to come up with approximate mode shapes and natural frequencies. Okay. So we will spend quite a bit of time over here. Here I will use, of course I did not mention, the main text I am going to use is vibrations of shells and plates by Werner-Sodel. Professor Werner-Sodel used to be a faculty at Purdue University. USA. He was also the chief editor of Journal of Sound and Vibration at some point. So this is the main text I am going to follow largely. Here and there I will switch text for some material, like the material for differential geometry from H. Krauss. Okay. So once we have the mode shapes one way or the other, mode shapes and natural frequencies one way, either closed form or approximate, then we will go for forced response of the shell. Okay. So in here we will look at different shells, plates and forcings and type of force applied. Okay. Then the last topic or last main topic would be connected systems. Connected systems. So once two systems are connected, for example a plate is connected to a spring, okay, how do the systems change and so forth, or a plate is connected to multiple springs, or how to put a line constraint using springs. Along this direction I want to constrain the plate, so how to do that using a bunch of springs. Okay. So, connected systems, the method is called receptance method. Along the way we will look at a few approximate ways of finding modes and natural frequencies of systems which do not fall under a strict shell of revolution and so forth. Okay. So, we will see what approximate methods exist or techniques exist to the extent possible, and I will also use for the Rayleigh-Ritz part, a textbook called the Rayleigh-Ritz method for structural analysis. By S. Ilanco and L. E. Monterrubio. So, I will use these texts. In addition, I will also use some journal papers. Especially for the Rayleigh-Ritz part and so forth. Now, this is an advanced topic. So, one should have had a vibrations course, okay, one lumped vibrations course, and a course on solid mechanics. And I will not restrict it to any particular group, but I will advise that this is largely meant for masters and PhDs and PhD students. One thing very important that I should mention here is that we are talking about thin plates and shells. And what does that mean? We need some typical empirical numbers. Okay. So, if let us say I have a plate and some typical dimension of the plate is A, let us say, okay, then we will consider let us say thickness to be, so the dimension, typical dimension is A and the thickness is H. Okay. So, if we have this number, let us say 8, so we are less than equal to 8 here and we are greater than equal to 8 here, then we are less than equal to 80 here and greater than equal to 80 here, and let us say till 100. So, this is my A over H, okay, A over H values. So, if A over H values lie in this range below 8, that means H is reasonably large, then we call it the thick plate region, thick plates. then between values 8 and 80, okay, thickness starts to reduce. So, this region we will call thin plates in some approximate sense, and then once we go beyond 80, this is called a membrane. Okay. Membrane has only capacity to stretch, okay. It has no bending stiffness, no bending stiffness. It takes the load only in tension, it can handle a load only in tension, okay. Whereas plates have bending stiffness, they have bending stiffness, bending stiffness, okay. Now, having given these ratios, what is the physical parameter that that tells us that we are in the thin plate or not? Okay. So, we will consider the vertical shear strain if we have a plate, okay, if we have a plate and let us say this is the one direction, alpha 1 direction. I have not introduced the coordinates yet. So, this is the 2 direction. So, what we say is that the vertical shear strain, which is epsilon 1 3 and epsilon 2 3 are 0. Okay. And what that further relates to in a physical picture is that if we have some structure, let us say this is a beam, okay, and then it bends, okay, let this section it bends, and as it bends, this plane section, okay, rotates and becomes like this, remains plane, and normals to cross sections, remain normal after deformation. Okay. So, this realm of dimensions I have given, and this physical behavior and these physical effects, that is the realm of thin plates and shells, thin plates and shells. And one more thing with respect to shells is that the thickness over R, radius of curvature. So, the thickness, this is a thin shell, so the thickness over the radius of curvature say measure from the middle surface is less than 1/20. That is also a criterion for thin shells. Here also the vertical shear strain will be 0 and these phenomena will hold. Okay. So, that is important to know. Thank you.